And we'll go from the current slide. Oh, we may even turn on the projector today. Well, we might if we have a... Where is the... Ah, there it is. Cleverly disguised. There we go. Okay, while that's coming up, let me go over just a few fairly minor announcements just to let you know in case I don't want you to make a special trip to find an empty room. Normally my office hours today, on every Tuesday and Thursday, are from 11:15 till 3:15. Okay? Today, however, we have a faculty meeting at 2:30. So, and here's Michaela. So a little before 2:30, like 2:20, 2:25, I'll be heading over to Ethel Hall building. Fortunately, it's on this campus, so I don't have to drive to the other campus. So my office hours today will only be 11:15 till around 2:20, 2:25, something like that. Okay? Then I'll leave the faculty meeting early. Oh no, because I've got a class at 3:15. So anyway, but I'll be in class from then on. And let's see, don't know of any other major issues coming up. Any questions on anything we've done so far? All right. Well, now this isn't good. Okay. What's that?
Where's the projector right at?
So again, there's a... Oh.
You just gotta hit source. And it should come up.
If it doesn't, it's dead. No, I'm just kidding.
Then you go to your... Is it computer?
Computer.
Do it again. Here it comes. And maybe it's HDMI 1. That should work. Oh, nope. HDMI 2.
This has been weird this whole time I've been here. I mean, most days it's been fine. Ah, there it is. Was it something you did or I did?
I think it's something you did.
I think so. There we go. I'll lay it down. Yuck. There we go. Why does it do this? I kind of want to blame the people who tie this cord in a knot. I don't know if this coax cable can handle that kind of twisting. Maybe it can, but it bugs me. All right, we had everything. So let's minimize this. Morning. What's that? Yeah, okay, got it. Thank you. And Dimitri came in, wasn't it? Anyone else come in while I was fiddling with the projector? All set and ready to go until the projector wouldn't work. Okay. So, any questions on anything we've done so far? There's some new people here. Now, this in your text is example 8. These are slides that I downloaded specifically to have the current slides, and they don't seem to be current. Okay. Jake is here. Okay. sure if I already got here. Okay. So let's see if we can move forward. This is example 8 in your text, even though it says example 7 here. All right. Yeah. All right. Cody, right? Okay. All right. Example 8 in your text, even though this says example 7. Remember the last thing we did, I hesitate to even touch this thing, it's been so sensitive this morning. Every polynomial of degree n greater than 0, the constants don't count here, with real coefficients can be written as a product of linear and quadratic factors. Okay? Even if it's a 15 degree polynomial, you can get them all down to linear factors or quadratic factors. Now, that's as long as they have real coefficients. The reason for that, any roots or solution that happen to be imaginary, complex, okay, then, did you get in? All right, okay. All right. Mommy. One second. Skyward. That's good. Oh, you hair today. That's why you had me fooled. Okay. If I'd have waited till you sat down, I'd have known it was you. Okay. There you are. Okay. I think I got everybody so far. Okay, so every polynomial of degree n greater than 0 with real coefficients, that's the key here, can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. If the quadratic factors have real zeros, factor them into linear factors, okay? But if they have complex zeros, then leave them as quadratics, okay? Because any time you have a complex zero for a polynomial with real zeros, what's true about it? If that's a zero of the polynomial, what do you know also is another zero? It's conjugate. So they always come in conjugate pairs. Those can be multiplied together to give you a quadratic factor, and those will have no real zeros. So that's our task here, is to find all the zeros of this. Oh boy, this is going backwards. Okay. Remind me? Evan's got it. All right, got it. Now, this is sort of going back to what we did before. It's not quite doing the thing. We were just talking about factoring, and this is finding zeros again, which should have been earlier. Now, they do tell us one thing. Okay, there's a couple things here. What do you notice about the polynomial? Fourth degree polynomial, that's good. So it should have how many roots? 4 roots. Some of them may be complex. Guess what? They already tell us one of them is. So what does that also tell you? Yes, there's another complex one. So then it may have up to 2 real roots, or it'll have another pair of complex roots. We don't know. But it will have 4 roots. 2 of them will be complex. And now, why can I say that? Why can I say that with such assurance that we know we won't have more than, that we've got to have another root that's complex conjugate, and if there are other complex roots, that'll be the other 2. Why can I say that? What kind of coefficients do we have? Yeah, coefficients. They are real. They're real, right? Well, yeah, but that's all right too. They're real coefficients. If one of those had an I in it, all bets are off, okay? That may have been the only complex zero. Or it may have had all, well, yeah, we already said that's a possibility. So if it has real coefficients, then you know that all the complex zeros will come in conjugate pairs. So It says find all the zeros. There is 1 0. They told us already. Did you just tell me what the second 0 was? 1 minus 3i is the second 0. So, we found 2 of the 4. How do we proceed from here? Any ideas? Fresh out of ideas this morning. Huh? What can we do to find the rest of the zeros? Okay, very good. Let's start with factors, because if you find factors, you can find zeros. So, what would be the factors characterized by those 2 zeros? Rather weird ones, but true. What factor results from this? This is x equal that, by the way. What would be its factor? X minus 1 minus 3i, and from this one, x minus 1 plus 3i. Okay, we found 2 factors. There they are. What can we do with them? I don't like them in that form. I don't care for those little eyes. Okay? Big eyes, I like them. What can we do? Multiply them together, okay? Because they're complex conjugates, what does that guarantee you will have? Yeah, we'll have a quadratic factor with all real coefficients, okay? Because these are complex conjugates of each other. So let's multiply those together. Here's the easy way, I think. Okay, rewrite this as x minus 1 plus or minus 3i, right? And those are complex conjugates of each other too. And what would their product be? X minus 1 plus 3i and x minus 1 minus 3i. What's their products become? Oh, it must be a Thursday. Okay. Alexi, right? Huh? Yeah. Okay. All right. Anyone think of an easy way to multiply those? Okay, you square the first one, x minus 1 squared, which would be x squared minus 2x plus 1, and then negative 9i squared, which is positive 9 plus 9. Anytime you're multiplying 2 complex conjugates together, it's the first squared plus the second squared, okay? Unlike other conjugates that are not complex, and it's the difference of the 2 squares. But because that I squared is a minus 1, it's the sum of those 2 squares. And this then simplifies to be x squared minus 2x, really hard math, plus 10. All right.
Right there, you said you multiplied it by itself. The first one you multiplied it by itself to get that.
Okay. Okay. Let me catch what you're saying. Are you saying multiply these by themselves?
Yeah, is that what you did to get that?
Yeah. What I did to get this, I regrouped these and saw that this is the same in both, and then plus or minus 3i. So I said, well, that would be the complex conjugate of this with itself. Not just the complex conjugate of those. This is the complex conjugate of that. So yeah, multiply this together. That gives you this part. Okay, and then multiply this together, and it gives you that part, add them together. So, what do we do now that we found it? Any other questions, by the way? Great question. Okay, now that we found that that has several names, it's a quadratic factor that's irreducible in the reals, meaning in the real number system, you can't factor that. In the complex number system, you can. We just know what it came from. But in the real number system, it can't. And here's Cameron's. Okay. All right. So what? We've got a factor. Everybody agree that's a factor, right? What do we do from here? In your text, this is example 8. On the slide set, this is example 7. I don't know why. Previous edition, it was 7, but the slide set should reflect this edition. So what do we do now? Divide. Excellent. Think we can use synthetic division? Nope. This is not a binomial. The coefficient of the leading term is 1, but the exponent is not. Going to be that favorite good old long division. X squared minus 2x plus 10 divided into the dividend here, x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. Is that sing-songy enough for you? Okay. Where would you begin? All right. Reggie's here. All right. Where would you begin? Yes, begin on the left side rather than the right side. X squared will go into x fourth how many times? X squared times. Then what do you do? Multiply. X squared times x squared is? X to the 4th. X squared times minus 2x is? Get out of there. X squared times minus 2x is? Minus 2x cubed. Now we do what? Change signs and add. Make that a minus, make that a plus, add. These go away, just like we expect. What happens there? Negative. X cubed, then you do what? Bring down the plus 6x squared. Now we divide again. X squared into minus x cubed will go minus x squared. Okay? No, minus x. Where did I hear a square? Okay, minus x. Okay? And then you do what? Multiply. Minus x times x squared is minus x cubed. Minus x times minus 2x. Oh, wait. Whoa, what are y'all doing? Y'all are completely out to lunch today, aren't you? I could have left that. You forgot to do your last term. What were you thinking? Okay. On the first one, x squared times x, and then x squared times a 10 is plus 10x squared. Y'all get straight here. Then we change signs to add, so that plus 10 becomes a minus 10. Okay, and then we add. All right, and that did become a minus x cubed, and that becomes a minus 4x squared, and then you bring down the plus 2x. I'm going to have to keep an eye on y'all guys. This is just never. Okay, now what? We multiply. Remember, we already divided. I already had it up there. Okay, and minus x squared times, minus x times x squared is minus x cubed. Minus x squared times minus 2x is? Okay. Minus x times minus 2x is plus 2x squared, and minus x times plus 10 is minus 10x. Okay, that's a minus there. Okay, now what do you do? Change signs and add. So that becomes a plus, that becomes a plus, the middle one becomes a minus, if a pen would work. All right, there we go. Now, let's add what you get. 0 is exactly what you wanted to get. This becomes a negative 6x squared plus 12x. Bring down the negative 60. All right, are we going to make it? Let's see. What do you do next? Divide. X squared and the negative 6x squared will be negative. Yes. What's that? All right. It'll be negative 6. And then you do what? Multiply. Negative 6 times x squared is minus 6x squared. That's good. Then you do minus 6 times a minus 2x is plus 12x. That looks pretty good. And here's Walt, right? Okay. Okay. And finally, minus 6 times a plus 10 is negative 60. Ding, ding, ding. We have a perfect factor. What do we do with it? What's that?
They all cancel out when you flip the signs.
Okay, yeah. When you change signs and add, those all go to 0. That means we have a perfect factor here. No remainder. So that this went into that exactly that many times. What do we do with this now? Yes, let's see if we can factor that. X squared minus x minus 6. Will it factor? We hope so. What's the person? Okay. Here's Ryan. Somewhere. All right. Good deal. Okay. Will that factor? What's the first only possible factor for the first term? X times x. Then we look where? Sign of the last term. That's a minus. That tells us what about these two signs? One's negative, one's positive. You want two numbers because they're different signs that multiply to be 6 because they're different signs. Their difference is 1. Negative 3 plus 2. Excellent. Okay? Now, that gave us the factors. They didn't ask for factors. Why did we get the factors? That will give us the zeros. What are the zeros then?
3 and negative.
X equal 3 or x equal negative 2. So there's 1 0, there's a 0, yeah, and here's a 0, and there's a 0. We got 4, that's all she wrote. Does that make sense? Use your factors, okay? Factoring zeros, x-intercepts, they all come out being this, related to each other. Use them to find each other. Okay?
So wait, what were all the zeros? I know the 2 just got X from the 0.
So again.
What were all 4 zeros again?
Okay. They gave us the first one. X equals 1 plus 3i. They said given that that is a 0. Okay? Then we knew because you had real coefficients that the conjugate of that would be a 0. So here's the second 0.
All right, got it.
X minus, I'm sorry. There it is. I knew I'd written it somewhere. Here it is. I put the check in the wrong place. It was in the mail, but never mind. Okay. All right. I put it there. I should have put it, oops, yeah, up here. There's the second 0. Okay? Okay? Once we get those two zeros, they were zeros, let's make them factors. Once you get them as factors, multiply them together, that gives you a quadratic factor. To get the quadratic factor into that, long division, unfortunately. Do the long division, you get another quadratic factor. We see if that can be factored, and sure enough it can, and that gave us our last two zeros. X equal 3, x equal negative 2. Now, in reality, they're giving you a 0 to begin with. In reality, we'd probably just have the polynomial and say, find the zeros. Then you use the rational zeros test. Oh boy, that's going to be a big one, isn't it? because the constant term has lots of factors. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus, they go on and on and on. But unfortunately our our leading coefficient is 1, so that's all we got. So we start going down the list, and ultimately we'd probably find -2 first, and we have to keep going down the list, and we get our +3. Then we wind up with the factor that looks like this right here. And that we try to factor, it won't. Then we try quadratic formula, and when we do that, we find out it has imaginary components. And that gives us our answer. So most of the time, that's how we're going to do it. This time, they were very kind to us, gave us the first factor to give us room to start working. Any questions on that? All right, there is a checkpoint at the bottom of the page. Please do that as soon as you can after class is over. Okay, I hesitate to move this, but I can't read my book. Ooh, okay, cascade. Okay. All right, moving on to page 158. An example 8, without knowing that x1 plus 3i was a 0, still possible. Yeah, we went through all that. Okay. So let's do example 9. Let's see if it's on the slide set. Ooh, by the way, I forgot. This one's on here, so let's clear all of my chicken scratch and see what because the complex zeros occur in conjugate pairs. Why? Because all the coefficients are real. You know that 1 minus 3i is also 0. There's our second 0. Okay? They're just rehashing what we just did. And Ron decided to show up today. Okay, good. All right. Good deal. Anyone else come in that I didn't catch you on the way in? Okay. That means that both x minus 1 plus 3i and x minus 1 minus 3i are both factors of f of x. Okay? So we take those two factors, multiply them by each other, but before we do, to make life simpler, if you just did it using these, and I wouldn't have, when we did it, we didn't even put the parentheses, so we had minus, minus, and minus plus here. If you were trying to do those, that's a 3 by 3, not foiling. You do this times this, this times this, this times that, this times this, this times that, this times that, and this times this times that, this times that. Ew, it's a mess. So, being good mathematicians, lazy as all get out, then we try to find an easier way. And that easier way is to notice that if you put the minus 1 with this, and leave a minus 3i, and the minus 1 with this, and leave a plus 3i, you wind up with a conjugate pair. And rather than doing 9 multiplications and adding them together, you do 2 multiplications and you got your answer. That's a good mathematician. Lazy as all get out. Okay? Try to find the simplest way to do the problem. Okay? So this produces x minus 1 squared minus 9i squared, because you square the first one squared minus the second one squared. And it's real easy to do the square of a binomial, x squared minus 2x plus 1, and then minus 9i squared is plus 9. 1 plus 9 is 10. There's our non-reducible quadratic factor, because it came from complex numbers. Okay? Take that, divide it into the whole polynomial, and that gives us this. Just like we did. I'm not going through all the steps unless someone has questions about it. Got them? Okay. That gives us another factor, another quadratic factor. We hope this one's not non-reducible. It may be, but it turns out it's not. We have these 2 quadratic factors. Can the second one be factored? We know the first one can't be factored any further except with complex numbers. Can the second one? Well, let's try it. Sure enough, it can. X minus 3 times x plus 2. Okay, so now that we have that last quadratic factor factored into linear factors, we know exactly our 4 zeros. The one they gave us, the one that's the conjugate pair of that because the coefficients were real, then we had x equal 3, x equal minus 2. Make sense? All right. So without being told that x plus 3i was a 0, you could still find the zeros by using synthetic division, well, rational zeros test and synthetic division to find the real zeros, negative 2 and 3. I just went through that with you. Then you could factor the polynomial this far and say, hey, once you did negative 2 into it, positive 3 into it, you'd wind up with that as a quadratic factor. You can't factor that straight out using quadratic formula. You find out it has complex roots. The radicand in the quadratic formula turns out being negative, so that has the complex roots. Okay. Now, they're skipping example 9. I was afraid they would. So let's go back and find some room to work. I think this will be about the best we're going to come up with. Okay, example 9. Write f of x, I just did, okay, is equal to x to the 5th plus x cubed plus 2x squared minus 12x plus 8. Okay, we're going to write that polynomial as a product of linear factors and list all the zeros of the function. Okay. Time out. If this winds up with complex zeros, I'm happy just to leave them as irreducible quadratics. So we don't have to go all the way to linear if some of them turn out to be complex. Okay? Where would you begin? All the possible rational zeros, is that what you're saying? Okay. And they'll be of the form P over Q, where P is all the possible factors of 8, which are plus or minus 1, 2, 4, and 8. Okay? And in your denominator, just plus or minus 1, because that's from your leading coefficient. A lot of those. All right? What's the easiest one to check? Plus 1. How do we do it? Add your coefficients, because when you put a 1 in here, that's 1, that's 1. This is 1, 2. 2 times 1 is 2. 2 times 12, minus 12 times 1 is minus 12. 8. Just add these coefficients. So what do we have? 1 plus 1 plus is 4 plus 8 is minus 12 is? Yes, we got it right there. X equal 1 is a 0. Okay. So, they're asking for factors. Why say x equal 1 is a 0? They weren't asking for that, were they? It tells you your factor. What factor does that represent? X minus 1, exactly. Okay, so what do we do with it? Say again? Oh, sure you do. Say again? He's a hard worker, I can tell, okay? I prefer, yeah, he hard worker, you, okay. So do synthetic division, 1 into what? Okay, and what are those coefficients? 1. 0. We're missing the 4th term. Okay, next. 1, 2, negative 12, 8. All right, good deal. So, do we have enough numbers there? How many do we need? We need 6. 1 more than the degree, and sure enough, we got 6. That's why that's 0. Check to make sure you got 0. Skip a line, draw a line. Then we'll do what? Bring down the 1. Take it from there. 1. 1. Well, y'all are stuck on 1s, aren't you? Okay. 2. Okay. All right, we needed Ashley to come in so that our projector will work. Okay. All right. Okay, we got the 2. What was next? 2. 4. 4. Negative 8. Negative 8. And 0. We knew that was coming because we knew it was a 0. We already said it was, but we needed to get to the next step. We needed to get our, what kind of polynomial does that represent? 4th degree. Okay. Now at this point, I don't know if you remember this, I keep warning you about it, we need to make sure we don't have a repeated 0. So we may need 1 again. But you remember how 1 would go? Add those coefficients. Let's add them again. 1 plus 1 is? Oh, high level math today. Yes, it works again. So we can do x equal 1 again. So here's our second linear, well, here's our second 0. The linear factor here was x minus 1. The second 0 is x equal 1. Its linear factor is x minus 1. Okay, so let's do a 1 here. Skip a line, draw a line. And what do you do? 1. 1. 2. And what do you get? All right. 4. 4. 8. 8. 0. We knew that was coming. All right. So now we're down to our second 0, x equal 1. Now, you want to check and see if 1 will work again. Could be repeated again. What you think?
We're good. I don't think so.
Not possible. Why? All these are positive. And again, nothing negative to add that becomes 0. So 1 won't work again. Don't even try. Now, I want to give you a hint. They're going to get to it later, but why postpone? Okay? Once you get all positives here, if you're dividing by positive numbers and you get all positives in the result, that tells you 1 is the biggest positive 0 you can have. Anything else, any of those other positives here, plus 2, plus 4, plus 8, they're going to make even bigger. So they won't work. So we found our 2 positive real zeros, x equal 1 and x equal 1 and x equal 1. So don't even worry with the positives anymore. Let's go to the negatives. What's the easiest negative to try? Negative 1. Let's try it and see if that'll work. Okay? Skip a line, draw a line. I'm running out of room, folks. Okay? Bring down the 1. Okay? What do you get there? Negative 1. 1. Negative 1. 3. Negative 3. Won't work. So negative 1 will not work. Let's try negative 2. Okay? Stealing my thunder there. Okay? Ooh, I lost part of my 8 too. Okay. Ooh, lost way too much. Okay. There's my skip a line, draw a line. There's the 8 that disappeared. And we're going to try negative 2. Okay, what does that give us? Negative 2. 0. 0. 4. Negative 8. 0. Ding, ding, ding. We have another one. X equal negative 2. Okay, what would be the factor associated with that? X plus 2. Okay. Now, what does that three number quotient tell us? It's a quadratic, right? Okay. And what is that quadratic? Okay. I should have been doing this all along. Okay, let's go back and refresh our memories. This one, how did that line disappear? I don't know how that one did. Duh. Okay. Now, this one represented a 5, x to the 5th. Once we did that division and got down to, that line disappeared too. Where did they all go? Where did you go, Joe DiMaggio? I don't know why they all disappeared. Okay. This one represented, if that was x to the 5th, this was x to the 4th, this was x cubed, and this was x squared. We stopped there. Why? We can use either factoring or quadratic formula, right? So what? Don't ever go past when you get 3 in your quotient. Stop right there because that represents a quadratic. So what quadratic does that represent? X squared. Say again. Plus 4. Set that equals 0. Can you factor that?
Yeah.
How?
On the other side, it would be plus or minus 2.
Okay, let's try that. Now, what you just move it over there? Okay, just move, oh, you subtract it. Okay, you don't just move it. That's the moving van, okay? We don't do that. Let's subtract 4 from both sides. And what does that give us? X squared equal negative 4. Say again? That, not just irrational.
Imaginary.
Yeah, complex, imaginary. You're absolutely right. Plus 2i and minus 2i. Okay? And like I said, I was happy getting you not just the linear factors. That would give you linear factors. Your two things over here would be x equal 2i and minus 2i. The conjugates of each other. Okay? All right. So those are the last two roots. You can make them as linear factors. I'm perfectly happy leaving this as x squared plus 4. An irreducible in the reals quadratic factor. That's all I want out of it. Okay? If you're going into the imaginary parts, you could write that, and the book wants you to, x minus 2i and x plus 2i. Those would be the last two linear factors. Then you have 5. That's all you got. Done. But I'm happy leaving that as a quadratic factor, x squared plus 4. All right. Any questions on that? Okay. Now, when you write that last one as a factor, these two, you don't have to, oh, that was probably my parentheses there. You do not have to write it twice. How could you write that? X minus 2, x minus 1. Getting my brain all crossed. Okay. X minus 1 squared times x plus 2 times the quadratic x squared plus 4. If you just want to save a little space and be really lazy, you could write it that way. Or you could write x minus 1 times x minus 1. That's perfectly fine too. Okay. Done? There is a checkpoint at the bottom. Please do the checkpoint as soon as you can. All right. Let's move on from there to other tests for zeros of a polynomial. Now, a couple of these will be very useful, and then you'll run into some I've already told you about. Okay? So let's start with this. You know that an nth degree polynomial function can have at most n real zeros. It will have n zeros, but some of them may be complex. So the most real zeros would be n as well. May not have them, though. Of course, many nth degree polynomials do not have that many real zeros because they have them in complex pairs, okay? Or conjugate pairs. For instance, obviously, f of x equals x squared plus 1, no real zeros, okay? Plus or minus I is all you got. F of x equals x cubed plus 1 has only one real zero. Now, they didn't tell you how they knew that, but it's true. One real zero. Okay? All right. I don't know really why they threw that in there, but it's true. Okay. The following theorem is called Descartes' rule of signs. Ever heard of Descartes before? Don't get Descartes before the horse. No, that was something else. Okay. Anyone ever hear of Descartes? Do you know that beautiful graph that we have? What's it called? The Cartesian coordinate system. Named after Rene Descartes. Okay? He was also quite a philosopher, and one of his most famous sayings, many of you may have heard of, I think, therefore I am. Rene Descartes. Okay? Well, he also came up with this rule of signs which sheds more light on the number of real zeros of a polynomial. Here's how it works. Write down your polynomial function. F of x is equal to a sub n times x to the nth plus a sub n minus 1 times x to the n minus 1 all the way down to a sub 2 times x squared plus a sub 1 times x to the first plus a sub 0. That's your polynomial. They need to have real coefficients. If they don't have real coefficients, don't use the Descartes rule of signs. We're not going to have any without with complex coefficients, so you'll be able to use it. Also, the a sub 0 can't be 0. Okay? If the a sub 0 was 0, then it's not there. Then factor out an x, and then you will hopefully have one that the last term is not 0. Okay? Keep doing that until you get something with a polynomial where the constant term is not 0. Okay. Now, the thing they didn't say directly, but I'm going to say it directly. Be sure this is in descending order of your powers. Standard form, right? Don't have them all mixed up there. So if they are in standard form, descending order of the power, polynomial written that way, then what you do, the number of positive real zeros, this is so bizarre that this is true, but it is, number of positive real zeros of f is either equal to the number of variations in sign of f of x or less than that by even integers. Boy, that's sort of difficult sounding. When you see the actual work, you'll see, okay, this is pretty easy. Now, if you want to, that's the number of positive real zeros. For the number of negative real zeros, what you got to do is go back to the first polynomial, plug in a minus x here. So if this n is even, that's not going to change anything. This sign will stay the same. If this n is odd, then it's going to change the sign for that. Okay. So this one would stay whatever sign it would be. This one would change because you put a negative x in here. Put a negative x here. Negative x squared is positive x squared. So that doesn't change the sign. Negative x would change the sign of that one. So the odd terms will change signs. The even terms will not. And that's all that happens. Then once you have the f of negative x, count its number of variations in signs. And the number of negative real zeros will either be that number or reduced by 2, or reduced by 2, or reduced by 2. Okay? The variation in sign means that two consecutive coefficients have opposite signs. Okay? So, they're easy to detect. The definition there is sort of vague. So let's do one. When using Descartes' rule of signs, a zero of multiplicity k should be counted as k zeros. Okay? So that last one that we had, x equal 1 and x equal 1, that was two positive zeros. Okay? So, for instance, here's a polynomial. How many variations in sign does that have? This is positive. How many changes of sign? Positive, negative. Negative, positive, 2. 2 variations in sign. Now, the next thing we would do, so that means we either have 2 positive real zeros or 0 positive. Reduce it by 2. So either 2 positive real zeros or no positive real zeros. Okay, hang on to that thought. Next thing we're going to do is put in a negative x. This would become negative x cubed. This would become positive 3x, because both of those are odd, and that stays a positive 2. So then you have a negative, positive, positive. How many changes of signs? 1 and only 1. Guess what? You do have 1 negative real root. Can't have 0, you have 1. So you've got to have at least 1 negative real root. You may have 2 or no positive real roots, but you will have 1 negative real root. Okay? So let's see what we got. Oh boy, they did all the work for us. Shame on them. We don't want them doing that, do we? Okay? So what I'm going to do is pretend you didn't see this, okay? What would be one possible 0 for that polynomial? Do your rational zeros test. What are your possible zeros? Possible zeros? Plus or minus 1 or? Yes, the factors of this, because that's a 1 there. Plus or minus 1 or plus or minus 2. We know that one of those, one real 0, will be a solution. One negative, so either the negative 1 or negative 2 could possibly be a solution. Okay? All we know is they're real. See, we're only doing rational zeros there. If that turned out to be an irrational number, it could be a negative irrational. We don't know that. All right. Now, which is the easiest one to check? 1. What do we do with the 1? Add the coefficients. What do you get? 0. So we know 1's a 0. X equals 1's a 0. Guess what? Remember we said we have 2 variations in sign, so you either have 2 or 0 positive real zeros. Guess what? You got 1. There's got to be a second one out there. The second positive 0. It could be 1 again. It could be 2. Okay? So you keep doing to see what you get. Guess what? It turns out being 1 again. Okay? And then you got to find your negative real 0, and it happens to be x equals negative 2. I wish I could do that all for you, but they got it all over the board here. Okay? There's our 2 positives. There's a 1 negative. Zeros, not factors, 0. Okay. They did too much work for you there. All right, so here's, in your book, it's example 10. On the slide set, it says example 9. It says, determine the possible number of positive and negative real zeros of that function. They don't ask you to find them, just what are the possibilities. So for positive real zeros, what would you do? First thing you do is make sure it's written in descending orders of the power. Is it? Yes. Okay, so therefore we're fine there. Then what do we do? Count your variations in sign. Three or three or 1. Subtract 2 from it. Remember, you always subtract 2. Okay? So it either has 3 positive real zeros or 1 positive real 0. Guess what? You've got to find 1 positive real 0. May not have but 1, but if you find 2, keep looking until you find 3. Okay? That's all they're asking for here, the numbers of positive and negative real zeros. So what do we do to determine the number of negative real zeros? What do you consider? Negative x. No, negative x. And what would that be? Say again?
First one will still be positive.
No, because that's an odd number. Put a negative x in there. Negative x times negative x is positive x squared, but then times another negative x is negative x cubed. So that would be negative 3x cubed. Next. Negative 5x squared, because you put in the negative x times negative x is positive x squared, times negative 5 is still negative 5. Okay? X squared. Next. Minus 6x minus 4. Okay? Now notice what happened there, folks. I'm trying to show you the easy way to think of it. The odd exponents will change sign, plus to minus. The even exponents stay the same. Odd exponents change sign, even exponents stay the same. Okay? That's the easy way. Or you can think through it. Now, mind you thinking. How many negative real zeros do we have? Possible. How do you get it?
Well, it doesn't change sign.
It never changes sign, so there are no negative real zeros. Don't even bother looking for them. So when you do your rational zeros test, just do 1, 2, 4, 1, 3. Don't bother with the plus or minus. The minuses are not going to work at all because you know there's no negative real zeros. So there's certainly no negative rational zeros. Okay? See? You can cut your work. Be lazy. Thank you, Rene Descartes. You enabled us to be nice and lazy here. Okay. That's all they're asking for here. They didn't ask you to find them. They just said determine the possible number. So here we have, what was the answer for positive? How many possible positive zeros? Second?
1.
No. 3 or 1. Always reduced by 2. Here, 0 negatives. 3 or 1 positive real zeros. And this is 0 negative real zeros. Okay, that's all you can tell from Descartes' rule of sign, but that will make your hunt easier. Okay? Number one, you can just throw out all those negative rational zeros. They're not going to work because there's no real zeros, no negative real zeros. Okay? Now, I think that's all they do. If they do any more, we'll come back and do it. Okay? Let's erase that. See what they get. The original polynomial has 3 variations in sign. A plus to minus, a minus to plus, and a plus to minus. 3 variations in sign. That means up to 3 positive real zeros. Sure, they didn't say that, did they? Okay. Then when you put in f of minus x, and they carry it out, maybe I should have done that, that would be a negative 3x cubed minus 5x squared minus 6x minus 4, no variations in sign. Therefore, from the Descartes rule of signs, polynomial f of x equal blah, blah, blah has either 3 positive real zeros or 1 positive real zero. Okay? 0, no negative real zeros. Okay. Now, if that was a 5th degree polynomial, it would be, if it had 5 degrees changes of sign, that would be 5 or 3 or 1. You always keep subtracting by 2 until you get to 0 or negative numbers. Okay. Got it? So that's all they wanted us to do in example 10 in the text, 9 here. There is a checkpoint. Please do that one. Oh, then they showed there is only one. Okay? They graphed it and showed this. Now, and it happens to be x equal 1. Could we have told that? Plus 9, minus 9, yes, we could have told you that. Okay? It has a 0 at 1. Now, what you can't tell is that if it has 3 or not. That's where you keep doing your synthetic division, and if all the signs get such a way that you know that it can't go any further than say, well, no more rational zeros, you still don't know if there are no real ones. But guess what? If you find that 1, x equal 1, what are you down to? quadratic. And then you can tell by factoring or by quadratic formula, right? So yeah, we didn't need to do any more synthetic divisions once we found one. And we knew one was one. Okay. Another test for zeros of polynomial function, okay, related to the sign pattern of the quotient that's left, okay? The last row in synthetic division array, that's your quotient, with remainder if you have it. That test can give you an upper or lower bound of the real zeros of the function. Okay, now what do we mean by upper or lower bounds? A real number C is an upper bound for the real zeros of F when no zeros greater than C exist. That makes it a C an upper bound. Similarly, C is a lower bound when no real zeros of F are less than C. So if you have a negative number here and you know it's a lower bound, nothing out there, don't go any further. In your rational zeros test, don't go anything below that. Or if you have a C over here that you know is going to be an upper bound, don't look for any more. Once you determine that's an upper bound, stop. Now they haven't told you how to tell if it's an upper bound. Let's see. Here's the upper and lower bound rules. Okay? Let f of x be a polynomial with real coefficients. That's always the case here. And a positive leading coefficient. We don't start out with negative leading coefficients. Positive leading coefficient. Now, suppose that f is divided by x minus c. Using synthetic division, in other words, put the c on the outside and do your thing with that. If this c is a positive number, positive 1, positive 7, 3/2, whatever, but positive, and when you do the synthetic division, each number in the last row is either positive or 0, then C is an upper bound. Don't go any further. Now, if you have changes of sign there, keep going with higher C's. At some point, you'll reach a C that all positives in that bottom row stop. Can't go any further. Okay? But if C is less than 0, if C is a negative number, negative 1, negative 3/2, negative 17, whatever, and the numbers in the last row are alternately positive and negative, then, and 0 entries count either as positive or negative, then C is a lower bound, so don't look for any ones below that. Okay? So that's what I think I've pointed those out a couple times to you. Let's see some real examples of those. Whoa! They don't give you a real example of those. Example 11 is in your text, so let's back up so we find some room to write. Okay, I think that will be it. All right, let's get example 11 done. Find all the real zeros of f of x is equal to 6x cubed minus 4x squared plus 3x minus 2. Okay? Find all the real zeros of that. That was what it asked for. What's the first thing I'm going to do? Easy, easy test. Just did it. Second? Okay, easier than that. Yes, Descartes' rule of signs. What does Descartes' rule of signs tell us about that polynomial? Second?
Changes 3 times.
Yeah, the sign changes 3 times. What does that tell us?
It's going to be 3 or more
positive real roots, okay? That's something you can write down right now. Descartes' rule of signs says 3 or 1 positive real root. Zeros, whatever you want to call it. Okay? Get out of there. Okay. Then a fairly easy thing to do would be alpha of negative x. And that would be negative 6x cubed minus 4x squared minus 3x minus 2. Guess what? 0. negative real roots. Okay. So either 3 or 1 positive real roots, no negative real roots. That's going to help us when we go to the next step, which is what you were starting to do before. Is what? Yeah, the rational zeros test. Okay? So what I'm going to do is write my solution there up above, because I'm going to need all the room I can get. Okay, so we know we have either 3 or 1 positive real roots, and no negative real roots. Okay? So when we do rational zeros test, we're looking for ratios that are P over Q, where P is what? Say again?
Plus and minus 1 and 2.
Okay, except guess what we can do now? Forget the minus. Forget the minus. So it'd be 1 or 2 in the numerator and denominator 1, 2, 3, or 6. Perfect. So let's list them all. I like the whole numbers best, so I'll do 1 and 2. I'll do that one. Okay, now you start listing the fractional numbers. I did 1 over 1 is 1, 2 over 1 is 2. 1/2, 1/3, 1/6, 2/3. Done. Okay? You could have 2 over 2, but that's 1. We already have that. 2 over 3 is 2/3. 2 over 6 is 1/3. We already have that. So those are all your possible positive rational zeros. No guarantee these are going to work. Okay, remember that, because all it says is real zeros. Okay? Which is the easiest one to do? 1. What does that result in? 2 positives are 9. Your 2 negatives are 1's not going to work. So don't even bother with it. What's the next easy one to do? 2. I would say that's why I always start with the thing. So let's go with 2. So what do we do with 2? Put it outside the house. What goes inside? 6. -4. 3. -2. Do we have enough numbers? Yes. 1 more than the degree. 3 is the degree. 4 numbers. You got it. Skip a line, draw a line, and what do we do now? Bring down the... Okay. Oh, I dropped it. Okay, never mind. Okay. Next. Is what? 12. 8. 16. 19. 38. I think this isn't going to work, but what do you get there? 36. Now this is sort of a duh moment here, but we'll have it anyway. Guess what? This was a positive number. You went into it. All the signs are positive. That means 2 is the upper bound. Well, guess what? 2 is your upper bound anyway, okay? You aren't going to have any beyond 2. So that didn't work. Unfortunately, we're going to have to try something else. 1 didn't work, 2 didn't work, so here comes our fractions. Okay? So let me erase the 2, erase these, and erase those. All right, which one you want to try next? 1/2. Okay? Now actually here, for the purposes of this example, I would start going low now. Okay, so I think I would start with 1/6. I'll explain why. Remember, we're testing our upper bounds test. So if we start low, I like to do the whole numbers, we did them. But I start low here. Once we get a fraction that everything's positive, then you don't have to do any more fractions. If you started with 1/2, except for 2/3, that's your largest fraction. So you're not going to eliminate anything. So let's start with 1/6. So you brought down the 6, and what do you do next? Multiply, and what does that give you? 1. -3. -2, is that what you said? Yeah. Right? Excuse me. Okay. -2, right? No, -1/2, you're right. Oh, there's a 1. What were you thinking? Okay. -1/2. Okay. Ooh, this is getting that ugly, isn't it? Okay. It's not ever going to get any better either. So we can stop here. Okay. And we already see we have a change of sign, so 1/6 is not our upper bound. But let's stop with it anyway. Okay. Second? Is that going to be it? Okay. Cheater. Okay. Working ahead. Okay. So we're going to have to go all the way to 2/3. Is that what you're saying? Since we're running out of time, we'll follow Patrick's lead here and go up to 2/3. Okay. What's 2/3 of 6? 4. Add 0, 0, 3, 2, 0. Ding, ding, ding. We found the 0. 2/3. Thank you, Patrick. Okay. And guess what? You couldn't go any higher. So if we'd have done this one first, we wouldn't have had to do the 2. We knew that it wouldn't work. Or we wouldn't have had to do 1 either, because it wouldn't work. But anyway, what you're left with is 6x squared plus 3 and that's equal to 0. Guess what? No real solutions. So after that, we remember what we said? 3 or 1 real zeros? We found our 1, and that's the only one. We should have done all those, but we ran out of time. But you'll find that's the case, that 3 or 1 real zeros. Oops, only 1, and that's x equal 2/3. Okay. And they factored it, and it's x minus 2/3 times 6x squared plus 3. Okay. There is a checkpoint. We'll begin next time with the application. However, I know y'all want some homework exercises for the weekend, because you would hate to have no math to do this weekend, so let's get some. Any of the odds 9 through 13, they're all at Calc Chat. 9's at Calc View. Do either 15 or 17, they're both at Calc Chat. Do any of the odds 19 to 27, they're all at Calc Chat. 25's at Calc View. Do either 29 or 31, they're both at Calc Chat. 29's at Calc View. Do either 33 or 35, they're both at Calc Chat. 37 or 39, they're both at Calc Chat. You can skip 41 to 45 if you want to. You can skip 47 to 50 if you want to. Try to do either 51 or 53. They're both at Calc Chat. 55 through 59, they're all at Calc Chat. 55's at Calc View. 61 to 71, they're all at Calc Chat. 69's at Calc View. 73 to 77, they're all at Calc Chat. 79 to 85, they're all at Calc Chat. 83's at Calc View. 87 or 89, they're both at Calc Chat. Maybe we can stop there and pick up the rest of them. Okay.
Video on Blackboard of the cartoon group.
I don't have a separate video. This one will be up there later today. Yeah.